Good afternoon. Am I audible? Okay, good. So first let me start by thanking the organizers for inviting me. I wanted to come last time as well, but due to conflict of schedule, so I couldn't make it. So at least I'm happy that this time I could make it. This is also first time I'm actually giving a talk in a setting which is predominantly dedicated to mathematics. I would not claim even to be an applied mathematician. I'm a material science person or a metallurgist, if you will, trying to use some mathematical concepts to maybe build models that have some predictive capability. Okay. So what I'm going to do today is give you a really broad picture about how people model plasticity and mechanical behavior in materials with crystal structure that has hexagonal closed packed materials. Okay. And in particular I will focus on a mechanism that is called deformation twinning, which is a step more difficult than what is commonly responsible for plastic deformation, that's slip. Okay. So with that, maybe I'll first tell you who I am. So I am an assistant professor in IIT Madras, been there for about now 6.5 years. I mostly work on mechanics of microstructures, okay. With the idea that in principle I should be able to link mechanisms at multiple length scales. I should say so far I am only sticking to continuum, maybe down the lane I will diverse. Before that I was a postdoc at Los Alamos National Lab for about close to 3 years, working again on microstructural effects, and I got my PhD in 2010 in Catholic University Leuven in Belgium on mesoscale heterogeneity and polycrystal plasticity. Maybe this is not a bad place to say that I have not done a single experiment during my PhD, so it was completely simulations. So one particular emphasis that I would like to pay already at the beginning is what I tend to call as a microstructural approach towards mechanics of materials compared to the current phenomenological approach. Okay. So the most approaches towards mechanics, not all but most, and traditional ones typically are phenomenological in nature, and they somehow are not in a position to have a really good predictive capability as far as anisotropic response is concerned. Part of it is because continuum mechanics people or a lot of mechanics people tend to treat material as a continuous media. So it is not subdivided into grains, or crystallography is not accounted for. So if you account for that, like what the metallurgists tend to do, if then you have an approach which is more microstructural in nature, that intrinsically gives the models ability to predict things in a better manner. Okay. It of course depends on the problem that you are solving and more specifically the material that you are interested in, but because I come from a metals background and pretty much all the processing that you do on metals induce certain amount of anisotropy, one of the goals that we would always like to do is, can we incorporate that anisotropy and can we actually predict that anisotropy as a function of prior processing. Okay. And this is something that happens at both at an engineering scale, where you are interested in actually seeing how the mechanical properties would vary as a function of loading direction. This is of practical importance, and also at a very small length scales, where we would like to know what is the local stress state in a zirconium cladding surrounding a nuclear reactor, because that is what dictates the formation of hydrides, which will eventually lead to failure of this component. So understanding crystallography about and implementing that is helpful. So just to be clear, when I say structure of the materials, it's what we call as a microstructure. This is a very colorful image that is obtained from electron backscatter diffraction. The point being here, each of these are individual crystals and they have a different orientations. Okay. Each color represents the same orientation, let us say. Traditionally metallurgists relied on 2D planar cross sections that you cut. Of late you are now in a position to actually get in situ 3D microstructures from the synchrotrons, which gives us better statistics. So earlier what people would do is look at the 2D section and make assumptions about the 3-dimensionality of the microstructure. Maybe use some statistical correlations from a 2D or between 3 mutually perpendicular planes and say this is the statistics that is followed. So the underlying 3-dimensional microstructure needs to follow the same statistics. Now we are in a better off, but this is again a very niche, very few people in the world can actually do such experiments. So to be clear, the purpose for us to do models or describe material behavior in terms of mathematical terms, for me the first thing is it is sense of validation of whether I understand a particular phenomena correctly. Okay. But my funding mostly comes because I will be in a position to come up with models that would be useful for industries to predict realistic forming operations. And also there is a demand, we are just starting on this, is to see if we have ability to develop diagnostic capability. So if you have a structural component in place that has already been in use, can we predict what would be its lifetime, or can we predict at what time it's time for us to change the component without really taking the component out and testing it. And this is the last buzzword that people have been using, and in mechanics and materials community it goes in different names. You can either call it use of data analytics or machine learning and things like that. The idea is how best do we leverage the models that account for the microstructures to predict new processing routes, or in fact as a matter of fact to predict the new material systems themselves. Because I am not in the business of predicting new material systems. For a given material system, I am more interested in what happens to its properties and microstructures as a function of processing. Okay? And that would be something that we are doing there. So pretty much my group and I have been working in each of these components. Okay? There is the next few slides are essentially to set up the jargon that is typically used in microstructural mechanics. So you have to bear with me even if it's a little bit didactical. When you come across models that incorporate microstructural information, or other words called micromechanical models, the classification of the models is essentially based on the amount of information that you take from the microstructure into your models. Okay? So if this is your microstructure, the first level of the models is the so called mean field models. That means you are making an assumption that the underlying field, whether it's a stress field or a strain field, is continuous in a domain, a physically distinguishable domain. In this case, if you have a microstructure like this, if each of this is a grain, you are assuming that the stress field inside a grain is essentially homogeneous. It need not be a grain, it could be a region even smaller than a grain, but that's something that you are kind of saying you are averaging it over that particular quantity to get an overall response. And one of the first models is with the assumption of the fact that whatever macroscopic strain you apply, every grain experiences the same strain. So you maintain strain compatibility between different regions, but you lose the equilibrium of the regions. Okay, so this is what is called as a Taylor model, where
in that sense you don't take care of the particular shape of the grain.
Absolutely, yes.
Because if it is not something like that,
we are not going to do that. So that is why that's a good point. So this is actually statistical models. In fact, when we describe this material, essentially it is bunch of grains for us with no spatial correlation between them. Okay, and we can say, oh, each grain takes the same amount of strain, even though we know that it's far from truth, but this is just an upper bound approach towards the problem. Okay, so that's what it is. This is a Taylor model, which kick-started the whole process, and it's the same Taylor who actually came up with the idea of dislocations present in the materials. So we revere him and start from there. That's one way to go, where we say there is no influence of the deformation of one point in the microstructure with respect to the rest. On the other hand, you have the so-called grain interaction model. Say, instead of discretizing the microstructure as a set of grains, why don't we discretize a set of grain boundaries? Because then you are forced to say at a grain boundary, if you have two regions, different crystallographic regions, you can satisfy the continuity conditions and then say the overall response of the material is the averaged response of a bunch of grain boundary segments. By doing that, what you are doing is you are saying a region in a microstructure is influenced by its immediate neighbor. It need not see a long range field, but its immediate neighbor is important. So these are what is called as grain interaction models. Okay. Then you have the other class of materials where you say it's not the short range order that is important, it's actually the long range order that is important. Okay. So that means what you say is if you take a grain, because this is embedded in the microstructure, but we don't have the flexibility of incorporating every feature of the microstructure, we are going to assume that a given grain is embedded in a homogeneous media which has the properties of the average microstructural features. So this in principle is kind of extending the Eshelby mechanics to a polycrystal, the elastic Eshelby mechanics to a plastic problem. Okay. So, and these are the models that people, particularly anyone who is looking at microstructural mechanics, use quite often. Okay. The good thing is, despite a lot of assumptions that you are making and gross simplification of the underlying concepts, they are extremely efficient in predicting one of the most important parameters, that is the plastic anisotropy. So, if you take a bunch of piece of material, you deform it, the directionality of the eventual properties is something that it can do a reasonably good job. It is not going to do quantitatively, but qualitatively you would know we are within the ballpark figure about it. So, in that sense it is pretty good, and of course it is computationally super efficient. So, all you are to doing is essentially in this, but in both of these cases it's a simple simplex algorithm, and it can do pretty quick. Okay. This is slightly more time consuming, but it's maybe 2 or 3 times more than that, but still. You have a question?
Sorry, what is the difference between the Taylor and the self-consistent? In the Taylor model, you don't adjust the field self-consistently?
No, we don't. So, in the Taylor model, all we do is we say here is a grain, it takes exactly the same strain that you are applying to the polycrystal. So, there is no equilibrium satisfied anywhere, the fields are not iterated anywhere.
But it's not that different from the other case, except that in the other case you minimize it something, but only one, let's say,
yes.
only that global field.
Yes, it's so in this case you still iterate the fields because you are satisfying the local equilibrium between the inclusion and the media.
But the media is unique.
Media is unique, but once you, let's say you iterate over all the grains, then you are also in a position to update the properties of the media, right? So, it is self-consistently updated. So, that is the thing. Okay. Yeah. So, pretty good models, and these are quite often used even in the industries. The negatives, so as I told you, while it does a good qualitative job, if you want hard numbers to be as close as possible, then you are in not so good grounds here. Now, as a matter of people who are looking into it, you have to make several assumptions, right? Is the local interactions important? Are the far field interactions important? We don't know. So, you are forced to make assumptions about the macroscopically applied strain and the local strain in the microstructure, and that is something that is always questionable. You can go lower bound, upper bound, decide what you have to choose, but it is okay. Now, interestingly enough, while these do a good job of macroscopic predictions, there is very little insights that you gain about the material response itself, because you are ignoring the spatial continuity. So, if someone were to ask a question, given a material, where exactly would a crack nucleate? Now, this model will not do that, because for that you need to know what is the spatially varying fields. This can't do that. Okay. But anyone as a first year grad student, the first thing is expected to do is to code this in MATLAB. If you want to do Taylor code, it takes no more than about 100 lines. Of course, for him to get there it takes 100 hours or 100 days, but eventually this allows them to understand how do you incorporate crystallography and the mechanical response. On the other end of the spectrum, you have what is called as the full field models, which is a no-brainer. Essentially what you are saying is, we don't make any assumptions. We have a domain, we know its microstructure, we are going to discretize it, and then we are going to solve for the local stress and strain fields. The most common way to do it is the finite element method. And you know the boundary conditions that you apply. If you know at every integration point what is the constitutive response of the material, then you can pretty much get this, right. So, this is a 3-dimensional microstructure, and this one is a simulation where you have the local stress fields. No assumptions made in the sense that whatever is the mathematical model that you are using in a finite element method is the assumption. That's all there is. Okay. Of course, by doing this, you can easily imagine the computational resources that are required. These are extremely expensive compared to the other ones, and quite often we use commercial finite element softwares, and then we write our own subroutines that describes the material response for the underlying crystal structure. In the last decade or so, I would say maybe 2 decades, we have been using another approach which is based on fast Fourier transforms. This was originally proposed by PSUK in France to calculate very efficiently, a computationally efficient way, the effective properties of composite materials. Instead of using finite elements, particularly for materials which have very high contrast, can we get the effective properties very quickly. And then about a decade later, or Sukeva I think 98, yeah, and then Ricardo about 2000, 2001 extended for the polycrystals. And so we have been, I've been using, so I was with Ricardo during my postdoc, so I've kind of gotten that path. So in effect this is a computationally efficient way of solving the same field equations, except that you solve for the strong form of the equations rather than discretizing it, making it a weak form and discretizing it. So I am not going to go into the details, but what is the most interesting thing is the computational efficiency, that is the whole point, right. So if you compare for an FEM and for a spectral method, you have at least an order or two speed up for a same computational domain. That is very good. The disadvantage, I should also already tell you, is that this particular method using Fourier transforms actually has a solution only when your boundary conditions are periodic in nature, because you are actually solving the compatibility equations in an integral form by discretizing the Lippmann-Schwinger equation, and you have a solution for it only when you have periodic boundary conditions. So you can't do arbitrary shape changes or bending. Okay. So for RV calculations for small repeating unit cells and you want to understand what is happening internally, that is a good way to go. So when you come across microstructural models, you still have a lot of people using FFT, finite element models. FFT models has traditionally been niche because there are very few groups who have been working on it. In the last few years, I think there is one open source software that people have been using it, so you will also come across this. So just a quick word on crystal plasticity and what it means. So I will say the traditional way, this is your potato on which you do the kinematics, let us say. You measure a stress strain response, you try to do the curve fitting, okay, and then you say, oh, this particular material response is represented by K and N. In a crystal plasticity model, we say this is not a homogeneous blob, we have a bunch of grains, okay. This is the microstructure. Each of that is a single crystal. Then we identify for that particular crystal structure what is the mechanism responsible for plasticity, okay. And in regular FCC materials, we know that it is due to motion of dislocations on certain planes along certain directions. So if you have this information, the underlying microscopic phenomena responsible for plasticity, it could be motion of dislocations, it could be phase transformations, it could be twinning. If you have that information, then you are actually able to link that back to the macro scale simulations. So that is the idea. Crystal plasticity implies you are talking about a stress and strain relationship at a single crystal level on a slip system. That is the whole point. There is still some amount of phenomenology involved, of course it is not ab initio obviously, but you are accounting for the underlying microstructure and that is the goal for it. Okay. The whole crux, I have, yeah please.
So the previous slide, so is it a good method like if you have like very long, large crystalline domains, like if you have in a sample only few crystalline domains?
Absolutely. So the size and the shape of the grains is not going to affect it. So if you have large grains and few of them, if you choose to discretize them numerically, this model is something that is implemented at every point, even inside the grain. So let us say if you have large grains and you have the finite element mesh, because this is only a constitutive model which tells you what is the stress for a given strain.
It takes into account the, like along which axis?
Yes, absolutely. It takes, this is precisely the beauty of it. It takes into account for that.
But also the plasticity intra-grain?
Yes, it is possible.
So, because you are not forcing some kind of compatibility in the grain?
Yeah, so the image that I have shown you here, so here for example, what I am doing essentially, or what people tend to do is, if you are one element, at that point you impose your constitutive model, but the field continuity at the grain boundary itself is taken care by the finite element simulations, right. So we don't have explicitly any new constraints.
So it's like 2-3 different materials
Absolutely.
sharing a boundary where it is rigid, transfer of
That
yeah.
precisely. So in effect you can treat it if it's 1000 grains, it's a 1000 material composite model. Each composite model has a different anisotropy axis. That's about it. Did I answer the question?
You were referring whether, for instance, is that if the grains sleep one against the other, if there are defects?
Then you can't do
This
that.
is what I'm saying.
So
The grain, the defects, when the plasticity in many cases is because the grains, they friction one with the other.
so you're talking about grain boundary sliding.
Okay.
So
Grain
yes,
sliding.
yes, that we cannot do. I mean, there are frameworks that allow you to extend this, but in the existing models, at least I do not do that. But there are few groups who actually look into it and say perhaps you need to have extra set of boundary conditions at the grain boundaries. That's yes, that's a limitation.
Or you can create an interface condition between two grains.
Precisely.
So those will be representing the interface property.
Yeah.
Yeah, like a point there.
Yeah. So one example I can think of is, for example, people who are trying to understand delamination at the grains. So one easy way to do that essentially is they take continuum elements and they insert what is called as a cohesive zone element, and it comes with its own constitutive property. You say for a certain traction opening, you essentially open up that particular boundary. So that depends a priori on deciding what exactly should be the model for the interface region, and that allows you to then take it forward. Okay?
So here, each grain, you will be able to separate the equations from the system, the square coming from this system.
Absolutely, yes.
It's possible to differentiate.
Yes, that I'll show you the slide. That's the purpose of this slide. In a very crude sense, this is probably the only mathematical slide I have. You should pardon me. I am coming to a math institute and not showing too much of math, but I think my point was to kind of show the physics of behind it. So the point is, if you have at a given point in a material the local velocity gradient, the plastic velocity gradient, the assumption is this is accommodated by a process of shears. Okay, and you have alpha is a slip system which has a shears plane and the direction information on it, and this is accommodated by sum of all possible shears along all possible planes and directions. Okay. So this is the crux of the problem that we tend to solve. This is imposed to us. We know this information. This is basically a geometric tensor that describes a local slip system in the local reference frame. We would like to know what is the shear rate on a given slip system. Now, not all the 12 slip systems in an FCC material, you have about 12 slip systems, not all 12 contribute. The essence is which of the 12 actually contribute and how do you identify them. So this particular quantity tells you how much slip is occurring, and the B and N are the slip plane direction and things.
Shearing is having a sign. Are you having some positive and negative?
Okay, good. So I'll answer it right away. There's some slide coming. No. That's an interesting point. So what exactly does a shear physically imply? That's the question that answers your thing, right? So here we are talking about a dislocation motion on a slip system. Now for a dislocation, whether you are moving forward on a slip system or backwards is essentially the same thing.
No, but the overall, suppose you are pulling it apart.
Yes.
It will slide in mostly in one particular way, and if you are pushing it, compressing it, it will be in opposite.
So
Locally there will be pulling and pushing as well.
no. So that is the can I use the board? That helps probably. So let's say you have this, right, and you have a slip system on which a dislocation is moving forward. The only stress responsible for this particular motion is the result shear stress on this plane along this direction. So if I take sigma ij, this is the result shear stress. Okay, so B is a slip direction and N is a slip plane normal. So this result shear stress is responsible. Now it doesn't matter to this particular dislocation whether the macroscopic stress is tensile or compressive. Okay, In the same way, whether a dislocation is moving in this way or in this way, it has equal probability of motion. That means the physical process of dislocation motion itself is not perturbed by whether it is moving forward or backward. That is one of the beauties of slip or the glide process of dislocations. So that is why we do not account for necessarily for the whether it is moving forward or backward. The reason it is interesting that you brought it up, because I am going to spend a whole lot of time on another mechanism by which plasticity occurs, that is deformation twinning, and that is unidirectional. For that, only a forward shear is considered as twinning, and backward shear is not even possible. Okay, so the directionality of the slip, thanks to you, now we could clarify it here. Okay, so all right. So this particular equation that you see here is the typical power law equation, except that here you are saying a shear or the strain on a slip system alpha is linked to the resolved shear stress. So whatever quantity that I have written here on that particular slip system, okay, and then you evolve it as a function of strain, the material hardens, and you have an equation for it. Are you still with me, or you're okay? So that's about it. Okay, so that's the only math you will see, hopefully. So just to be sure, to put it in the right place, so this is where we tend to stand. It's called mesoscale or the polycrystalline plasticity, because these days having a slide like this is mandatory. Whenever you talk about material models, you want to identify where you stand with respect to the other people who are doing the materials models. Okay. So now I'm coming to the crux of my talk. So that's about hexagonal closed pack materials. Okay, these are important materials technologically, right? So you have applications across the board. So if you are interested in automobile industries, lightweighting is one of the things, and magnesium alloys, which happen to be HCP, are quite actively considered. For people coming from nuclear sector, zirconium alloys are the first line of defense from radiation, and for aerospace sector is titanium alloys, which gives you good strength to properties. So there's a lot of funding associated with this particular class of materials, but these are extremely notorious to actually understand. Okay, I'll tell you why that is the case, and I'll try to make the case that these are hard materials to model. We have talked about slip. In hexagonal closed pack materials, there's one more deformation accommodating mechanism, that's the twinning. The fundamental difference between slip and twin, while it is already clear, in the process of slip you have one or two, one part of the crystal displaced with respect to the other, and you might have a series of parallel planes which are slipped. And slip is kind of quantized, because the amount of distance a slip system can move is decided by the interplanar distance. Unlike slip, a twinning usually results in a domain. So when you do a slip, it's very hard for you to say this part of the material is slipped and this part is not slipped, just looking at the microstructure. When a twin occurs in a material, the one thing it does is it kind of splits the domain in which you are dealing with into three different parts. You have the original parent, and then you have a twin domain, and then you again have a parent. So in this case you see you have a parent grain, and this is what is called as a twin domain. The reason it's called as a twin is essentially if you look at this particular plane, you see that there is a crystallographic twinning that is happening across this particular plane. Now this is a very, very important mechanism in HCP materials or hexagonal closed pack materials, and I'll spend most of it. So these are a bunch of, to make life a little bit more complicated, in HCP materials you don't have just one slip family, you have multiple families which can glide with respect to each other and in different directions. Unlike in an FCC material you only have one family, HCP you have at least 4 to 5 different families. So it's a keep on piling up problem. And then there's another issue. For twinning, because you're talking about a finite domain in a material space, then you have to think, how does it come to be? We don't know yet. In fact, even atomistic models are still not in a position to tell what leads to twin nucleation. That's a $1 million question in material science at least. right now the assumption is there are certain nucleus that perhaps are there in the grain boundaries. We do not know what are the conditions under which they form a nuclear, a lamella that is big enough for it to grow. And once a twin forms, it even increases its volume with deformation. So it is not just the formation of the twin, but its evolution with time that actually makes it even more difficult. Okay, so that is the basic story. There are a couple of things that I would like to tell before I start further, go further. Here is an example of a zirconia material. What all we have done is taken 3 mutually perpendicular directions and looked at its microstructure. These lamellas that you see here, so for example this white grayish one in a purple grain is a twin. So this lamella is a twin. Similarly, these two are twins, this is twin. So this is prominent, you can see them quite significantly in the microstructures. Okay.
Sorry, what way you say that it is a twin?
Because we can measure the crystallography.
Oh,
Yeah. So and from the morphology by naked eye we have used to looking at as twins. Yes.
How different is this from a structural plasticity transition or structural phase transition?
Sorry, I did not understand.
How different is this tuning from what occurs in the alloys that have a structural phase transition and change phase and go from martensite to austenite, from austenite to martensite?
I think in principle they should be same. I don't know.
The language that
I do not know if there is a characteristic shear associated with that particular twinning. Is there a shear also associated with those things?
yes, essentially.
And is there a small volume of strain that is taken?
Only some variants are allowed in given the
Yes, so it is still the same. So I think it should be more or less the same. Yes, yeah. Okay, so it probably similar. I have never looked into. So you're talking about martensitic like shape memory alloys and
Yes.
things like that. Yeah, I think they are pretty similar. But again, I'm not an expert, so I can get back to you once I look into that. Okay. Yeah. All right. So there are many questions associated with this particular problem. One is, let's say you are in a position to model just by slip. First thing is you have to identify when would you nucleate a twin in your material system. You have a finite element mesh, let's say, and it's slipping and everywhere is fine. You have to have a mathematical criteria to say, okay, at this point you are now going to nucleate a twin. We don't have an answer to what should be that criteria. Okay. Somehow we have something, let's say. Then the immediate question is, what should be the state of this newly formed twin? Should it have the same stress state from where it has nucleated? So you have a parent which has twinned. So what should be its stress state, or what should it be its strain state? Should it inherit the properties of the parent, or because it has just formed, should it start from a zero stress configuration? So these are questions that we don't know have answers to, and we have been trying to address, not me but pretty much everybody in the community has been trying to address. Okay.
so the way you showed the deformation, it seemed to me that it can accommodate shear better than, are you saying that? The overall shear, meaning not the local shear, but the way you made the shape, it looked like it deformed.
Yes, absolutely. So what happens is associated with every twin, so if there is a small amount of twin that forms, there is a characteristic amount of shear that is accommodating, okay, and that is a large amount of shear that it accommodates. So that is why what happens is when you have crystals, so low symmetry crystals, when you are applying stress on them, if there are not enough independent slip systems to accommodate this plastic deformation, their recourse is to actually activate twinning, because they can accommodate shears, and that is the thing. Yes.
and twinning is reversible somehow.
Sorry?
Twinning is reversible.
So I have to be very careful here. So twinning is a unidirectional thing. So if there is a stress, only if it moves in this direction, it is called as a twinning. Okay.
But when you go back,
But when you apply compression, so if you are doing tension, only one particular direction would lead you to a formation of a twin. Okay. If you are still applying tension, the backward direction is not going to lead you to twin. However, if you take the material, then compress it, then you have a process called as a detwinning. So whatever was the original twin is kind of subsumed, and you tend to get the parent grain. That's one thing. You had a question?
Yeah, so just in microscopic simulations, you can compute vectors, and if that is the case, then one can compute stresses and strains.
Slow. Can you speak?
So in microscopic simulations, is it possible to see this kind of phenomena, and then one can compute stresses and strains in that?
So the easiest thing to do is say we take a molecular dynamics simulation and then say we are going to nucleate a twin, and in that we don't have to have any criteria, right? We just the interesting thing is when you take a perfect crystal or initially a perfect polycrystal without any twins and start deforming it, people are still not able to get twins that easily. Okay. The way they are actually invoking twins is they are artificially perturbing the system so that they can actually get a twin. Now of course once you actually have a twin, then you can see what is the local stress state of it and things like that. But then the question is whether the stress state of the twin that has formed, is it altered because of the perturbation. So the way these actually the trick that people use to nucleate twins is they are going to have a stress concentration in terms of a dislocation which is going to come and hit the grain boundary, and then hope that there is a twin that nucleates on the other side. So it is still a bit ambiguous situation. Not to, I mean I do not have that level of knowledge to comment on that, but one thing at least I understand is if you want to trust the molecular dynamic simulations about these physical phenomena, one of the important parameters that it has to do a good job is predicting what is called as a stacking fault energy, and that means your underlying potential needs to be substantially rigorous for you to do so, because a lot of this process while I am smearing it out essentially depends on the dislocation reactions and their interactions, and that you can only do a good job if your potential is able to do a good stacking fault thing. And for hexagonal materials, potentials are hard to trust. That is my level of understanding. Okay. Okay. So stress state is thing. Then there is another thing, just to be, because I will be using this again, there is something called as a Schmidt factor. If you are familiar with it, if not, essentially this particular term, quantity that you have seen, is something that tells you, so in a twin there are 6 possible variants in hexagonal materials. Okay. So if we have to ask a question, which of these variants is most probably be active, okay, then we need to know what is the stress on each of these variants and whether it satisfies certain criteria. Okay. What experiments tell us is if you are only going to look at that particular criteria, then you are not going to account for all the twins that you see in the material. That is because you are only looking at a macroscopically applied stress and you do not have understanding of what is the local distribution of the stresses. So this particular thing, the Schmidt factors, if you have 6 variants, for each of these variants you calculate the so called Schmidt factor and then say the one which is most stressed is the one that is going to be active, or that particular variant is going to be nucleated. But we have seen cases where not the most stressed one, but the lower ones are also active. So we do not know what exactly is the reason for it, and about 30 to 40% of the twins are always the variants which are not the most stressed ones. So you have variants which are lower stressed. Okay. So what we are going to do is to tell you one of the approaches that is done is, this is like one model feeding into another model. Okay. One model trying to kind of encapture what might be happening in reality and how you can sync both the models. The idea is, because we want computationally efficient models, we do not want too much time consuming, can we do a one-off large simulations, gain from that, and then try to use that knowledge to feed it into the lower length scale models or the mean field models. So I will just tell you the common way. For hexagonal materials, the VPSC or the self consistent kind of models are very common. You have already seen this is what happens. You have to ignore this lot of animations, I just took it from my advisor's slides, so they are as is. Once a twin forms, assume that we have a criteria in place, then we are going to say we have a grain which has a parent which is a green and the other color is the twins. You have a way to account for the dislocations moving on the slip systems, and then you have a model to propagate the twins. What you need or what we did is to remove deterministic nature of the twin nucleation and make it slightly more probabilistic, because for one we don't know what's happening in the material, so just let's account for the underlying distributions of the fields and see if we can incorporate that in a simple way. The idea is straightforward. I think I will skip most of this, but here is the deal. We have applied stress on a grain, you are resolving on a plane and a direction on a twin, and for every variant you calculate this stress. We are still going to say, if this particular value hits a threshold value, a twin nucleates. That is the typical way it is done, as if mimicking the process of slip. But because we are talking about microstructural features and we are not capturing them, can we capture those in terms of some amount of uncertainty value element into the model? So there might be saying that there is some amount of fluctuations that is happening that we can incorporate. Let me see it this way. So if you have a grain, this is the polycrystal, we would like to know if and when a particular twin is nucleated in this particular grain. Right now we only have the average value in the grain. How do we account for the local variations of the stresses that you expect at the grain boundary? Okay. You make an assumption, maybe it's Gaussian or maybe it's uniform distribution, pick that up and add that to each of these variants. Okay. So if you have some estimate of the locally fluctuating stresses at the grain boundaries, then you can add to that and then make it possible and pick up a variant. What you are simply doing is perturbing the deterministic nature by accounting or physically justifying the variation in the local stresses to that of the grain boundaries. And to obtain what would be the local stresses, obviously we cannot do experiments, we can't really measure from experiments. So we do very large polycrystal simulations, look at what is the stress variations within each grain and then make an estimate of what stress fluctuations are. So this was kind of the first time people measured what would be the local deviation of the stress inside a grain from its average, and what is the nature of that distribution. I mean, we could assume that it's Gaussian, but there was no real proof, because if and when you look at the stress distributions over the entire polycrystal and take it out from its mean, it's never Gaussian. Polycrystals tend to have log normal stresses, but within a grain it turns out it's mostly Gaussian, and we don't know why that is the case. And there are some input. In fact, one of the professors is still looking at what is actually the nature of the statistical fields that you encounter inside the polycrystalline materials, and that's first thing you need to address before you start addressing the uncertainty propagation, let's say. Okay. We did that, and eventually for us the bottom line is, can we match experiments? Okay. So as a function of temperature we are able to match. So at 76 Kelvin, 150 Kelvin and 300 Kelvin we are doing just a macroscopic stress strain curve for a particular zirconium, and then you measure the volume fraction of the twin and you say, okay, the approach is good. Earlier I don't have the models, I don't have the predictions without the probabilistic approach, but they don't tend to fit all the temperatures with the same efficiency. So one of the things with the crystal plasticity models is, if you have any material parameters or model parameters, it's the same set of parameters that you use no matter what your deformation conditions are. If you are doing tension, if you are doing compression, if you are doing shear, you should not change your parameters. Unlike a phenomenological model, where for tension you might have one hardening coefficient, for compression you have another hardening coefficient. Okay. So that's one beauty of the crystal plasticity models, that gives you flexibility to probe in the entire strain space. No matter from where you are coming, your underlying physical models remain the same. Okay. Yeah. So one of the things is the textures. I'll skip this. This is okay. I like this particular work, so I am going to quickly explain this. There was an experiment that was done which in 2007 I think, and was published after 2 years of analysis. So it was the first time an experiment was done where you are monitoring a grain while it is being deformed in situ. Okay. So you send very high energy X-rays and you know the grain in its nascent state, and as and when you are deforming it, you are able to measure the average stress in the grain because you are able to get the lattice diffraction patterns. And then what you saw is that when twin nucleates inside the grain, what is the variation in the stress, and that is very, very important. So this led to a lot of interesting questions as to, first, the result shear stress on the twin plane along the twin direction, if this is the way it is going to, when the twin nucleates, so this is that of a parent grain, initially it is just 1, volume fraction is 1, but with deformation when the twin nucleates, when it does occur, the sign of the result shear stress inside the twin is that of opposite sign compared to the parent. That means you actually have some kind of contrasting shear stress acting of a newly formed twin. A twin forms, but then we have to account for whether it is welcoming, whether the parent is actually welcoming the twin or what is the constraint it is imposing on the twin. Okay? And at what stage, that in material science community you call that as a back stress. At what stage the twin overcomes the back stress and then becomes kind of independent to grow. When it just forms, it is still constrained, but then it has to push over and then start growing, and that is what we have seen here. When it forms, it is constrained, but then subsequently of course it starts growing, and this was not even thought of in the early stages. I mean, it is only after seeing the results it was kind of surprising that, oh, this is a phenomena that potentially can happen. So what we did was a very simplistic approach. We do not know when the twin forms, so we are just going to assume that at a certain stress level it is going to form. This is an approximation. So you have a parent grain with a thin lamella of twin that is formed, okay, and all we do is macroscopically apply certain shear stress and let the characteristic shear occur inside these grains. The most important thing, so this is the outcome of it. What we are plotting here, you can't see much, I will try to, is the twinning result shear stress. That is the result shear stress on the twinning plane along the twinning direction. If you just look at the lamella here, that is the twin, the rest of it is just the neighbors and the constraints coming from the other sides. This is the profile. If you go from one place to the other, this is how it varies. First thing, of course, it is not homogeneous. You do not expect things to be homogeneous, but more importantly, the stress drops significantly at the twin tips, the edges, and you apply further stress. You see what happens. Of course, there is an increase in the result shear stress, but that increase is predominantly in the region away from this. So the way to think of it this way is, you have a thin lamellar region and you want it to grow with further stress. Okay. For the growth to occur, you need to have positive result shear stress, and what you see is the variation here. So if you have a twin region like this, if you are going from here to here, this region, only this region is positive, this region is still negative region. That means the conditions for twin to actually grow from this are not favorable. So twin is actually locked in here because only the center part is the one which is favorable for it to grow. As a consequence, you start seeing these kind of lenticular structures, because wherever there is a boundary, the twin is actually seeing a negative result shear stress that does not allow it to move further, but away from it you start seeing a positive result shear stress. Of course, for you to overcome this, you need to apply a lot more stress to get over it. So one of the common features, in fact one of the earlier micrographs that you have seen, twins do not appear as two flat lines. That is numerical approximation. It is more probable that you will see a lenticular shaped twins, and that shape has to do with the fact that the local result shear stress is actually following a negative values, that is impeding the growth of the twin. And that was the first time we have actually shown numerically that without explicitly accounting for it, it simply comes from the fact that you have local interactions that is taking place. Okay. So I have too many slides, but I will see what I can. Okay, this is just taking the different volume fractions and comparing it with the experiments. This is the last thing I will show. Okay. What you did is, because we were thinking the local stresses are responsible for plastic deformation or formation of twins, we keep the same twin in the parent but change its local neighborhood, because we can do that, and then start seeing will that affect the average resolved shear stresses in the parent and the twin. And what we have seen, of course, is of the 6 that we have taken, one of the grains is such that you do not have the reversal of the shear rates. Not all of them have that. Okay. So you see all of these are negative signs. Parent, you have 2 negatives, 3 negatives, and you have 3 of them which are actually positive. That means the ones that you have seen in experiments, okay, while you have the stress reversal, it may or may not be that it's something that is observed for all the possible orientations. It very heavily depends on what you see in the neighboring side as well. It's not just the parent but also the neighboring one which dictates the resolved shear stress in the twin. Okay. So I think I will skip for the rest of it because I have too many slides going on. I will just put the conclusion slide. Yeah, I didn't know how to pitch the talk, so I just kind of kept it vague, but I am guessing it should be okay. Maybe I should put a blatant publicity saying that the part that we skipped in the talk was just published in Journal of Plasticity. I will be more than happy to give you my preprint or send you the PDF of the paper. Anyway, so that's about it. So. Sure.
Whether height differential diffusion phenomena can be taken into account in crystal plasticity?
Yes. So it's 2 things. Crystal plasticity accounts for any shear process due to motion of dislocations. If the dislocation motion is affected by diffusion, then as long as you are aware of that relationship, then it's possible. So you don't account for explicitly diffusion, you account for the effect of diffusion on the dislocation motion. Here the only dislocation motion I have considered or people generally consider is the glide process. If you were to account for climb process, right, then you need to account for the diffusion and you need to know the rate at which the climb occurs. That's possible.
It's a single phase material. Maybe some precipitates are there in the grain or interior. Whether it can be.
Sure. It does. So even though it's in principle it's a single phase material, as we described, it's a 1000 material composite model. So if you add 1001, it's not going to change anything, right? Because it's just at a given point in your mesh, you have changed your material properties.
And the interaction with the precipitate and the dislocation also we need to prevent. It includes the gas slip mechanisms, the recovery mechanism we have to include. Then the complexity in parametric optimization involves.
Yes. So, but then you are asking whether we can do processes that are only at discrete level at a continuum scale. So, for example, in this here, you are asking if a dislocation can cut through a precipitate or if a dislocation can loop through it. We do not account for individual dislocation behavior, right? We only account for the homogenized response of the dislocations on a slip system in a given unit time. So, if you ask for one particular process, an individual phenomena of a cutting of a precipitate, it's highly unlikely that you can model it. There are ways to do it, but not up to your expectations or satisfaction. But yes, there are ways where you can say, again it's very straightforward, beyond a certain most of the crystal plasticity or continuum mechanics applied to microstructures rely on one thing. Do you know the criteria for a particular phenomena to occur? If you know exactly the stress state at which a precipitate can be sheared, then you are good to keep it.
Here is the input full dislocations. Whether it will consider partial dislocations in the.
Again, this is one length scale lower problem, right. So, at a continuum scale, the gamma dot naught is only talking about the effective behavior of dislocations, whether that particular shear has to do with a full dislocation or two partials moving in tandem. It is not going to differentiate that.
Your limit factor will vary based on the partial and
Based on the partials,
means leading or trailing partials.
but the net will be the same. So, that is the point, right. So, if you have one partial moving, another trailing partial coming behind it, but if they move in tandem, the operation is same as one perfect dislocation moving. So, the Schmidt factor for that perfect dislocation is what we care, instead of splitting into these two. Okay, is that clear? Sure.
Standard question.
Sure.
How do you connect down to scales below? Is there a way to?
Yes, absolutely. First thing is, I have only talked about, see, let me start off with that question, right. If a dislocation moves on a slip system, I would actually like to know the mobility of the dislocation. That you can only get from discrete simulations. So, if you want to have some models or equations that tell you this is how a particular dislocation is going to move at a given temperature or strain, right, the only way to do is do molecular dynamics and have faith in them, and in our ability to actually homogenize those results and can feed it into that. That is one thing, that at least a low hanging fruit that I can throw at you.
Yeah, I have all the time trying to compare with the mathematical information, but
That's all.
I missed maybe something when you talked about what is the crystallographic structure of the twin-end domains. What is the crystallographic structure? If you do crystallography of that domain which is twin,
Yes.
what structure does it have?
It's the same crystal structure, yes. So, okay. So, you start with the HCP crystal structure. The crystal structure of twin is also HCP. So, it is not a phase transformation, no.
This is what
It is the same, it's a HCP is still HCP. Yes. So, there is no, the cost of the formation of the twin boundaries is very less actually.
But then what you are saying is that the original material is just one of the other variants.
Yes. Yes.
So this is just changing from one variant to another.
From one parent you have six possible variants, you should pick one variant, yes. So, the orientation is different. If you want to call variant as an, I'm assuming that when you mean variant, you are saying orientation. Yes.
So you have 6 possible?
Yes.
But originally it's in 1.
Yes.
And then you have 5 to go.
No, originally it is 1. For that one, you have 6 possible children. So, you have the original orientation. For that orientation, you can calculate 6 possible variants, and then it picks one of them. Yes. Okay.
And this is only possible for HCPs?
You can also see it for FCC in some particular cases. You can
BCC material?
BCC you do not tend to say. So, these are typically seen in materials, very few BCC, very few BCC actually I think they do it, but generally it is very common in HCP, somewhat common in FCC materials with extremely low stacking fault energy. So, if you take copper or brass, you tend to see them. Orthorhombic materials, uranium for example, beryllium, you see them. Or ice also has in hexagonal crystal structure. Okay. Sure.
For the dislocation critical results, you have some rules kind of bonding model.
I'm sorry? Yes. Yes.
Similarly, for critical results stress, what kind of model is it?
Okay. So, you know very well what I was talking about. Okay. So, we do not actually model hardening of twin interface.
Based on volume fraction,
Because I still do not believe that actually we are at a stage where we have a reasonable understanding to keep it in. My approach so far has been, if I do not understand something, I will assume it as a constant, rather until I have some basis for assume some linear behavior or something else. If not, it is better to start off with constant and remove that as a parameter than add more quantities to it.
same thing we used to consider those kind of model as isotropic bonding model in microscopic scale.
Yes.
But in this case, kinematic also evolve during kinematic one.
Sure. The hardening model is something that you can choose as long as you can say this is the critical resolved shear stress as a function of this strain, that is possible. You can have Voce models with kinematic terms as well inside.
Last question.
Some projection about fatigue if you want to do. So suppose you apply a cyclic load, do these models account for the fact that slip, once it happens in one side, it may not fully reverse even though you have reversed the entire deformation?
You have to force them to have it. So there are some.
Right now in this it is a complete.
So the one which I have described, it's completely reversible. But if you want to actually have a fatigue model, then you have to force the dislocation behavior to actually account for that, and people do that. Actually, people tend to do that. Yes. Okay.
Let's thank the speaker once.
Thank you.